So, good evening, everyone. My name is Rakesh. I'm a doctoral student at IIT Bombay. So, this session deals with the different types of casting process and its defects. So, this was the class that was supposed to be on 7th December, the Wednesday class, but due to some recording error, I'm making this class again. Okay. So, in this class, we will be discussing the different types of process casting as defects. So the main takeaway will be you should get an understanding of the casting process as well as the defects. So when there is a question mentioning any type of process, you should get into mind the complete picture of its working principle and the applications and everything. Okay. Without any further ado, let us continue the class. Okay. So as you can see, there are two types of castings broadly divided. One is the sand casting, and the other is the special types of castings. So this main division is based upon the types of casting and the complexity involved in making the casting product. So sand casting is very well known. So sand casting is very well known to you. I don't have to you know explain much. I will just mention the working of this casting. So, so in this casting, so basically we will have a sand which is mixed with the clay, iron oxide, everything, so that it will get the required strength to bear the load of this casting that we pour in. So once we get the sand, we make the pattern. We will have the pattern. We have the cap, drag, everything, and we keep inside, and we ram it so that we'll get the cavity. We design the gating system, the pouring machine, screw, runner, gate, then the riser design. So once you pour the metal, within after some time, it will get solidified. We'll break the mold and we'll take the casting out. We'll remove the gating systems and riser, and we'll finish up the final product. That's the main basic steps that are involved in sandcasting, and it's a mass production which is now being used, which is now automized. So they're completely automized. So there is no interference of human in making these type of castings. Mainly the engine blocks are mainly made by this casting process. So now let us discuss different types of special castings. Okay. So as you can see, so there are I have listed some number of special castings as you can see. So so one is the permanent mold casting, or gravity die casting, pressure die castings, centrifugal castings, shell molding, investment casting, or precision casting, mid cast process, or full molding, or blast form process. CO2 molding, continuous casting, or just stress casting. Okay. So let us discuss one by one. So the first one is the permanent mold casting, or the gravity die casting process. So as you can see in the right side figure, we have a this molds which can be opened or closed using the clamps made of the metal, and you directly pour the metal, and as you can see the riser and this runner and the particle line. Once the metal is poured, we can separate the casting by removing the clamps, and we get the casting out, and we can repeat this process. This can be very fast production. So this is simply the gravity die casting, where we are not applying any pressure. We are directly pouring with the gravity, with the help of the gravity. So when you come to the pressure die casting, also, and there is other type, high pressure die casting. We use very high amount of pressure. So generally we use a plunger in hot. There are two types, hot and cold chamber. Generally you use a plunger or a ram to push to squeeze the this metal into the cavity. So here is the cavity, as you can see. Okay. So these are two types. We have hot chamber, cold chamber. The distinction is that In hot chamber, the entire setup, the metal, molten metal, the plunger, the the nose, everything is inside the metal, inside the hot metal. Whereas in cold chamber, we will use a ladle and pour the metal into that cylinder, and we use a ram to push the liquid into the cavity. So, what the main difference, why to put inside the hot chamber, why to pour using a ladle? If you see in hot chamber castings, the number of steps involved are the very less, so the production will be very fast. Whereas cold chamber, it is the number of steps are increased, so the production rate compared to hot chamber are less. But there is a catch that in hot chamber you cannot use high very high metal, very high melting points of the metal. Only for low melting points we can use hot chamber, whereas in cold chamber we can use nominally the medium range melting metals. So that's the basic differentiated between the hot and cold chamber processes. So let us move to the next. So centrifugal casting. So the thing should come into mind when you see centrifugal casting with the pipes. So the cast iron pipes. So as you can see, we can make the hollow pipes very with ease. If you want to make this with the casting process, we need a core, and we cannot produce, and the length limitation also we have. But in centrifugal casting, these can be avoided. As you can see in centrifugal casting, we have a two rollers on the top, two rollers on the bottom. So these are the rollers, the blue things, and we have a drum rotating, that is the yellow, which was given in yellow color, and the hash color is the casting that we finally take. When you see in the left side view, so we have a drum rotating. Okay, and we put the metal in this. So this once the metal is solidified, we can easily remove the drum. We can enlarge the drum, and or we can directly remove the through this side with this. So there is no complexity involved, and we can continue the process. So it is so there are very limited number of steps, and we have very high yield in this. So there is no need of gate. There is no need of screw runner. So that yield we have is very high in centrifugal castings. You can remember. So now there are some other types of centrifugal. One is the semi-centrifugal and the centrifugal casting. So as you can see, both look similar, but in this is the entire product that we produce. Say a wheel used for the automotive. So this automobile. So the wheel, if you want, you can directly produce in the centrifugal casting. So just a pouring basin, and we have a cope drag, and as well as the cavity. But whereas in centrifugal casting, we can produce several number of casting products using this. So here you can see only two, but it can be any number. So we have a central screw and gates that was um providing the liquid metal into the cavities. Okay, this is the discussion about the centrifuging casting. So there are these different types in which this centrifugal casting is the very important. So let us discuss about this the other types of castings. One is the shell molding. So as you can see, we are using a shell in this for getting that cavity. So initially we have a sand which was mixed with some type of resin, which hard so that this will harden when you expose to any uh, hot plate or kind of things. So here we have a hot pattern. So as you can see, the design is already provided here, the cavity, and we invert the box. So the sand which is in contact with the hot plate will slowly get hardened. So when you reverse it, we will get a so the thickness is depends upon the time you and the temperature uh, parameters. Then when you get, we can easily this the ejector pins which will eject the shell. When you combine the two types of shell, they'll get the final casting. You can directly use it as directly you can pour the metal inside. So there is no need of patterning. There is no need of or ramming or nothing. So we can directly getting a product with a good accuracy with a limited number of steps. And after that, we can directly take out the shells and we can repeat the process again. So this is about the shell molding. So remember, we are making the shells out of the sand mixed with the resin. Okay. So investment casting, you might heard it a lot of times. So let us discuss one by one. So for initially, we start with the die construction where uh, yeah. So where we design the pattern using wax. So as you can see, we inject the wax and we get the pattern. So this is the pattern that we want. So next, so this entire structure where we have a pouring basin, we have a central sprue, we have a gates, runner and in gates. So everything is made up of wax. Okay, sorry for that. So once the everything is ready, we dip it in slurry coating, where it forms a thin layer of slurry, and then we do a repetition of 4 to 5 times of this stucco coating, where we this powder ceramic particles will adhere to the slurry and it forms a desired thickness. As you can see in this picture, we have a desired thickness, so which can hold the pressure and the weight of the casting that we pour in. So once the casting is so before pouring the casting, we have to uh, remove this wax inside it. So in this, it was taken into hot ovens and kept it and hold it for some time so that the complete wax is removed from the mold cavity. So once it was dewaxed and dry enough, so we put the metal directly into the castings, and followed by the removal of the shell using sandblasting or jetting, uh, then followed by the cutting the the central screw and runner ingates everything, and the parts is machined and further taken into the inspection. So this is the whole structure of investment casting and very important in exam point of view. It is also called as a precision casting because the product that we get compared to the sand casting are very the dimensional accuracy is good. So that's the reason, and we can get the net shape product, we can get large amount of products at a time. But the main disadvantage is that it has many steps to follow. So as you can see, the steps involved are very high. But this is also used for lot of applications nowadays. So next, before going to the this large form casting, let us discuss about this Marquez process. So Marquez process is nothing but instead of wax, if we use mercury, so which gives very high, even high dimensionality, so that the liquid mercury is cooled down below the room temperature, so that uh, it gets solid, it becomes solid, and then everything is repeated similar, and then finally it was heated up so that the mercury is removed from this the pattern, the mold cavity. So now let us discuss this last form casting. So in last form casting, as you can see, the pattern is itself made of the polystyrene pattern, which is a plastic material, say like thermocouple. Uh, sorry, not thermocol sheets, as you can see. So once it was once the it was made into the pattern shape, it was inserted into the sand, and it was filled completely. Then we will not remove the pattern. As you can see, there is no requirement of two patterns, split patterns. As you can see, there is only one pattern we are using, and we are not removing that pattern at all, and we are directly pouring the metal inside it. Even that pattern is inside it. So this pattern will get evaporated instantly when it comes contact with the molten metal. Oh, okay. So then, and there will be, and this once everything is removed, this will get the good quality castings without any with the minor defects, you can say. So this is the last foam casting, the foam completely expanded in this process. Remember it. So now coming to the final last three stages of this special types of castings. Okay, and so CO2 molding is nothing but we it's a so we have uh, this clay which is mixed with some type of chemical like uh, silica borate, some chemical, and we when gas is purged into this, CO2 gas is purged into this, it will convert into silica gel, which is strong enough to weigh the loads of the uh, you know loads of the castings. So we have different types, using a single probe, using a multi probe, and then using a big duct kind of things, and to make the pattern shape. So this is called a sebative molding. So the mold is mixed with some chemical and hardened using the CO2 gas. Okay. If you have any doubts, it's very simple. You can easily get the processing videos of these. You just have a look. It takes less than 2 minutes, and you can get a better understanding of these moldings. Then come to the continuous casting, very largely used in making slabs, say from iron ore or some iron, mainly from the iron ore, steel, cast iron, whatever. So it is the direct. There is no mold at all. So will not hit the metal and will not pour in the mold. We directly cool this mold, this liquid into the solid. As you can see, so there is once the melt is flown from the top, from the ladle to turn this, from turn this to mold. See, this is a mold, and it will continuously drag the way. So we have a rollers which will drag the sheets. During this whole entire process, the melt liquid will convert into solid. As you can see, the color difference. This is how we directly get the slabs. So this is a continuous casting used in a very high uh, these processing plants. So then comes to the sludge casting. This is more or less similar to the this, this shell molding, I can say. So in this we pour the metal. So initially we have a mold which was heated, and then it was added in the powder, and the rotation of the powder, so that the the sand will, which is in contact, will get hardened, and which is finally removed. Okay, this is the process of stress casting. So this was used for mainly for the hollow objects that we want to produce. So this is uh, the main special types of castings that we generally use. Okay. So mainly, so this class slash casting is used to cast non-isotonic hollow shapes from non-ferrous alloys such as bulb domes, artificial jewelry, etc., where accuracy is requirement is not critical. Okay, that is a main distinction from the shell casting and the sludge casting. Remember. So initially, the metal is poured in a metallic die, and the die is tilted to drain off the excess metal. After skin of the required thickness is obtained, the skin itself is the casting. Okay, so you can assume you take a suppose if I want to cast, so this is the my mold. Then what I do, I'll pour the liquid metal. So when it starts solidifying and forming some thickness, so at that time I will invert this complete thing, so that I will get, sorry, I'll not get this. When I invert this, the remaining which is in liquid state will fall off, and I will get this thickness. Okay, so this is my casting. So that is the sludge casting in this process. Okay. So until as I said, in CO2 molding as well. So the chemical used is the sodium silicate. Okay, as a binder agent in this. When this CO2 gas come into contact with this thing, it will form a very hard mass silica gel, which binds these sand grains together, so that the mold is hold it together. So if you want to see this reaction, sodium silicate Na2, let's say O3, and with water, when combined with CO2, we get sodium carbonate and the silica gel, which I'm talking about. This is the silica gel. Okay, that's the chemical. That's the whole thing about the CO2 gas. And this is the theory regarding different types of casting. You just have to remember the principle, simply how it works, and then you should remember the applications where we use and why we use. Here I discussed about 10 different types of special castings that were generally used in this processing industries. So now let us discuss the casting defects. Before that, I will give a 2 minutes break. Just free up yourself. Then we can start discussing about the different types of casting defects. Okay, so welcome back. Let us discuss different types of casting, which are important for the theoretical types of questions in GATE exam. So as you can see, I have listed some of the casting defects. Some starting from blowholes, shrinkage cavity, hot cracks, tears, mist and cold shed, rat tail, buckle, mold, punch caps, cap blisters, and pinholes. Okay, as the right side also you can see the figures, how the blowhole, how the different types of casting look like. So, so these the blowholes that occur due to the moisture present in the mold or the gas entrapment, and similarly for the pinholes, but the size and the group you can see, and mistron incomplete filling, mismatch where the cap and track are not aligned properly, and the drop you can see the extinction swell. So this is the actual dimension we required, but this is the dimension that we got finally. Metal penetration due to the loose and you can say cold shed, incomplete fusion, hot tears. So this is due to the uh, you know low, I can say, unyielded supports the directional cooling in direction. So not a directional cooling of the solid. Shrinkage cavity due to the occur during the solidification process. Wash and cuts. There's the extra portion and the slagging inclusions that occur. during the processing during the sand castings. Okay, let us discuss one by one. So initially the blowhole. Blowhole is like it's a smooth, almost spherical cavity formed due to the entrapment of gases because of low permeability of the sand. Okay, so initially blowholes. Okay, so the blowholes is the smooth spherical cavity. Uh, so when you pour the liquid metal into these small cavities, so if the permeability of the sand is less, so the gases which, so as I said, the solid has the solubility of gas in solid is less when compared to the liquid. So liquid has more gas absorption when it's slowly becoming into the, so when I take, so this is during solidification thing, this is the liquid and this is the solid, and this way it is getting solidified. Okay, so now I'm removing heat from this side, so I'm getting for understanding purpose. So this is the friend that is moving. So now what happens, so initially there will be some x% of concentration in a whole liquid. When the solid front is moving further, this solid will reject some the gas into this, say hydrogen for example, it will reject into the liquid. So the for each time the liquid concentration, the gas concentration in liquid will increase by some delta x amount. So when the solidification has moved sufficient enough, so this liquid will become very high saturated, say by saturated gases, so that it was able to form the a liquid drop, so liquid bubble inside it. And if you have this permeability of this the sand wall, if the permeability is good, this liquid can escape easily, as well as but if the permeability is not so good, this liquid these gases will be entrapped inside, and finally they get solidified, and they will be within the castings. So that's the reason why these blue holes occurs. So you have to remember the permeability of sand is also very important in this scenario. Okay. So the second uh, defect I want to talk about is this shrinkage cavity. Okay, this is something to do with the shrinkage of the metal when it solidifies from liquid state to solid state. So as you seen earlier also, so this is the mold wall. Okay, so these are the mold walls where the nucleation initially starts, and it gradually progresses. So what happens? The whatever the liquid at the center will be still hot, and it for because the solidification is starting from this direction, and this direction. So finally, scenario will come like this, such that there is no liquid present at the center. Everything got taken away by the solidifying front, and at the center we see at the center this position we see options of material as a shrinkage cavities. This is the defect known as shrinkage cavity, and this can be happen inside the metal also. It is not the way. It is not only present at the center. It can also happen in inside the casting due to the same effect. But inside casting, the distinction you can clearly see between this gas, the porosity more or less they are spherical, whereas think they are very rough, flat rough cavities. So this is due to the improper gating and rising systems. So you have to provide enough. So if this is taken away, if we can provide extra material using some riser, so that which will compensate this loss, then we can avoid this defect very easily. So next, let us move into the hot cracks or tears. Okay, hot tears. So these are the smooth edges, dull cracks formed due to the differential contraction of the casting. and only provision of if you provide the chills or the modification of casting design may eliminate these cracks. So let me take very simple structure, say I section if I am taking. So for easy understanding, so this is the casting I want. Okay, and I have a mold completely everywhere. So now when this is getting solidified, so what happens is that so this so at this portion you see some type of stresses because this try to pull the entire thing this side and this try to pull entire these things. Okay, you understand? During cooling, the shrinkage happens from the liquid to solid shrinkages. So when this happens, we get these residual stresses inside this component, which results in the cracks formation here or here, anywhere. Okay, this supposed to be happen in a solid blocks as well. If there is no you know very small, so the residual stresses it in bulk you cannot exactly see the this this phenomenon, but at the micro level you can easily see even less amount of force is enough to initiate the crack during the liquid stage. Okay, this is what about the this is all about the hot tears. So why this is happening is that so one is the so the casting design you have to keep in mind. So if you can provide chills, so the solidification changes and the direction of solidification changes. One is the casting defect, the other is the low melting point phases, such as iron sulfide in steel and hardening elements such as magnesium in steel, increases this tendency of hot cracking. Since they solidify initially and increases another increases the hardness, so that the flexibility is not so good in that casting, and it finally uh, results in the hot cracking. So this support we can easily call as unyielding supports. Okay, and if you have a long range freezing, also one more is that so where the fluidity is less. So this is also one of the reason for this type of defects, and this fluidity will also come in some other defect that I will explain. So the next one is the Mishran. So as you seen earlier also, so there was a casting like this with a step, and the filling stopped till here. So there is an incomplete filling of the casting. So this defect is called misrun. So the reason for this are low pouring temperatures, low fluidity, low permeability of the mold. Okay, so these may be the reasons for this misrun. So it was very clearly understandable, as you can see. So this uh, there is one more defect also. I will explain. So one more defect that you may easily confuse with, that is the shift and the misrun. So misrun is incomplete filling, whereas shift is due to the misalignment of this cope and drag during this split pattern casting. So don't get confused with these two types. So the next type of casting, very important casting effect, that is cold shut. This is also you can also hear the same type of defect in forming as well. So the this cold shut is like the incomplete fusion of two streams of liquid metals. Okay, suppose suppose we have a this is the system, and this is the cavity I need. When you pour this hot metal into it, into this, so it will initially comes like this. Then once it is at the level of this gate, so both it try to fill from the both the sides, and we will have a when we'll have a junction where these two streams of metal meets and they form this incomplete fusion kind of mark. Okay, so this is also due to the same reasons, you can say. So that is the permeability. The second one is the low pouring temperature. The third one is the low fluidity of the metal. Okay, this type. So these are more or less similar to what we discussed just before, that is Mistral, but there that casting is itself absent, but everything is present in this type of defect. But this incomplete fusion zone we observe in this type of defect. Okay. Let us move to this next type of casting defect. That is buckle and rat tail. So we have a casting like this, but instead of that we got this casting with also some type of protrusion of this sand inside like this, which looks like a rat tails. This is the buckle. So these are the types of expansion defects which occur due to differential expansion of the sand grains. Uh, so which differential expansion occurs in the sand that results in compressive and shear type of stresses uh, in the mold wall. So which so when you see this when this is in liquid state, it is very easy to deform that metal, that liquid metal. So it will get relaxed by pushing the balls into the castings. Okay, which forms the shallow conical depression, also called as a buckle. So this is the buckle which occurs due to differential expansion. When it comes to the ractals, when this ramming during the sand casting is not uniform, some small part of the sand forms a weakest region and it will be pushed into the molten metal, and then it forms in a deep depression, which looks like a rat tails. Okay, improper. So the reason I can say proper ramming, which results in a loose sands, and which will be included in the sand. So next is the mold drop and scab. Okay. So this generally occurs in deep castings. So this water vapor, which is present in the which is present in the mold sand, will get evaporated and moves up. Suppose I can show you a diagram. Okay, this is the casting we have. So now, so how this initially starts is, so the water vapor, initially this water vapor that formed during the evaporation of moisture from the models will get moves up to this top of the casting, and it will get condensed. Means it will form this water droplets, and it will lose this part of this mold walls. So this when this mold wall is weakened, and there is expansion of the differential expansion of the sand, so this which induce some compression shear forces. So this under these conditions we can really get a crack in the mold wall, and due to crack, and there is also addition of this self weight. So due to the own self weight, the sand of the at the times when this filling is happening, so meanwhile the filling is happening in this direction, this sand, this mold will directly will fall on this mold, this liquid which is moving upwards, which is known as mold drop. By the time the metal moves up to the top of the casting, so till say till here, so this mold will be get sandwiched between the top and liquid, and the mold will be present in here. So this is the big chunk of mold metal mold wall that is inside the casting, which is sandwiched between these two sides of the casting. And as well, this liquid metal will move into this casting. So the final casting I'm going to get is the kind of looks like. And also we have this mold. So this is called as This is the mold drop that we see. Okay. So this is the scenario which occurring due to this water vapor presence, then crack initiation followed by the drop inside the liquid that creates a shallow cavity that results in the defects cap. So this is the process through which this cap or this mold drop happens. So that's why, which is the main culprit here is the water vapor. So next move to the next type of defect. That is scar, blister. So these are due to the mold metal interactions with the where the permeability is low and the moisture is excess such that the instantaneous formation of water vapor exerts pressure on the liquid metal. This also uh, due to the same reason, but we will not get that much big scabs. Instead, we'll get this type of defects. Scar is a shallow depression, whereas if it is little deeper, we call it as a blister. Okay. So this the reason being excess water vapor. Okay. So this water vapor will insert a pressure on the casting that is being formed, and it forms this type of depressions. It is little deeper, we call it a blister. It is shallow, we call it a scar. So let us come to the final type. Is the pinhole. So these are the group of small within the small proximity. These are narrow deep holes which are formed mainly due to the hydrogen gas. So the reason is similar. So one thing is the permeability of mode where there is no provision for the gas to escape. The other thing I can say is the gas entrapment inside the casting. So how to remove is that you can use some degassing agents such as CCl4 is one of the disgas agent, or SAM. So these two you can more or less play with in order to reduce this type of pinhole. This is mainly this gas entrapment is this gas presence is cannot completely remove it. So we will have this limit PPI for with hydrogen for industrial standards. So it should be below that point in order to accept that castings. Okay, these are the different types of castings and different types of casting defect that I have discussed in this class, more or less. And one more thing is the slag inclusion I missed. So this is more or less similar. There is any improper ramming during, or if there is any loose sand, so this sand will get mixed with the molten metal and it forms these inclusions. This may be due to these sands, or while production during the processing itself. So sometimes there will be formation of the slag. So in the production itself, so suppose the liquid metal, there will be slag formation on the top. So you have to remove the slag before pouring into the metal. Otherwise, it will induce in this type of defects. So either due to slag or there is the inclusions near the sand also get mixed with the this mold and this liquid metal. So one thing generally what we see in regular practice is that they make a hole here instead of making sorry, they make an entrance exit here instead of making here, so that when the liquid is tilted, when this tundish whatever that we use when tilted, this slag will be here only, and the liquid metal will enter from here, this part, so that this will get entrapped in the top layer only. Unless we can easily clean it off if it is easily cleanable. Otherwise, we can make a provision like this to avoid the slag inclusions. So these are the different types of casting defects that are very important in the exam point of view, and these are the different types of casting defects that are generally discussed in this foundry technology. So if you have any doubts, we can discuss in the next class. So the next class is going to be a metrology class this Sunday as well as the next Wednesday. Uh, so if you are not familiar with this metrology, you can attend those classes. And if you want to get more insight into this casting types and defects, there is one course in NPTEL. So manufacturing process and casting, such as casting and joining, buying from IIT Kanpur, if I'm not wrong. So in these are the NPTEL lectures. You can just have a look to get more uh, information about these type of things. Okay, we have some time left, so let us quickly go through some of the uh, questions that we can easily discuss. So the first question, so in die casting process, the mold material is sand. So they are asking about the die casting process. The mold material is sand and the molten metal is moved by pressure. Okay. The mold material is metal. Okay. And the molten metal is poured by pressure. Okay. The mold material is metal and the molten metal is poured by gravity. The mold material is sand and the molten metal is poured by gravity. So die casting is completely made of metal, so you can strictly get this out. Then when come to the gravity and pressure, so here he did not mention which type of casting. So there is a pressure die casting or simply gravity die casting. So if nothing is mentioned, we can go for the gravity instead of pressure. Okay, that's the call you have to take. So both options is correct, but that is the call you have to take, because if you are using pressure, you have to mention pressure die casting. Otherwise, you can directly mention the casting process where you use gravity for filling the mold. Okay. So next question, in sand castings. So in general in sand, an expandable mold is used. Correct. A permanent mold is used, which is wrong. The molten metal is poured with pressure. No. The parts can be produced to net shape. No. In sand casting, it is difficult to push the products to the net shape, which can directly used in application without any for their processing. So these are already discussed in the previous class, which was uh, due to some error I could not upload this. I could not record this video. Say a pattern. So what is a pattern? So the mirror image of the part to be used seems to be correct, but there is some logic missing. An element in casting used to compensate for shrinkage, but what shrinkage is not mentioned. An element used to make internal holes in casting is wrong. That is core. Generally used the replica of the part to be cast. So this is the the most correct answer. It's not the mirror image; it's the physical part. And this when come to the shrinkage, so generally we have so many solidification, liquid shrinkage and solid shrinkage. So only during liquid shrinkage we can use riser, whereas for solid shrinkage we have to use pattern. So he did not mention which type of shrinkage using, but that is not the main goal of using pattern. The main goal of using pattern is to get the casting product, and these are the additions for this pattern for the so compensation for shrinkage elements, machining elements, and all of these things. So the next question is patterns are made somewhat larger than panel jobs to produce. This is called as, so generally we use the term allowance instead of using tolerance for this type of things, and commercial casting fix wrong, and draft is not the correct option for this. I'll discuss what is draft. Okay, then let me remove this. The shrinkage elements. So this talks about the shrinkage elements. Is directly proportional to the linear. So to answer this question, something you need this. So if I say delta L is the shrinkage elements, it is the formula. If you remember, this is the formula. Remember. Okay, these are the units I have written here. Is directly proportional to the linear quotient thermal expansion of the pattern, which is correct. Is inversely proportional to the length of the casting, wrong. Does not depend on the ambient temperature, no. Is directly proportional to the freezing point of the material, no. Does not depend on the length of the casting, no. This is wrong, which depends. So you can remove option 2 and 5. This is gone. This is gone. This is gone. So this is the correct option. Okay. So if you feel any doubts, we can meet in the next class and discuss. Thanks for watching. See you on the next class.